Welcome back to another video on linear algebra. Today, this lecture is going to focus on linear independence, and we're still going to continue with vector space and subspaces. And so we're just going to go ahead and get to it. Oh, before I start, this lecture would be or is much easier than the vector space and subspaces, but it does incorporate those things into this. So let's get started. So we're gonna first start off talking about linear combination. And before we talk about linear combination, we're just gonna have, or we're gonna work with a finite vector space that we're just gonna call V. And so we're gonna let a vector U exist in that vector space. And so vector U can be a linear combination of vectors 1, vector 2, all the way to vector k if they're scalars of c1, c2, all the way to ck, such that when you multiply that scalar with one of those vectors and you add them all together, it will equal to U. So another way to say this is basically, if we have a vector U, it is possible that there are certain other vectors that when you multiply it by a specific number and you add them all together, you can get that vector U back. And so that set of vectors v1, v2, all the way to vk is a subspace and is called the span of V. And so if a vector is a linear combination, so that means the set of vectors that span V can be altered in such a way to make a different vector, then that vector is linearly dependent. So in our example with the vector U, because it is a linear combination, then that vector U is a linearly dependent vector. And so what that means is that if you want to have a linearly independent vector, then that means that vector cannot be written as a linear combination of other vectors in that vector space. So for example, if you have a set that contains 1 x, x squared, x cubed, and then x plus x squared minus 1, well, the x plus x squared minus 1, that can be written as a linear combination of adding the x plus the x squared and then subtracting 1. And so the x plus x squared minus 1 is linearly dependent. And so that means it's a linear combination of other vectors in that space. That also means that the vectors 1, x, x squared, and x cubed, those are all linearly independent vectors because you can't add or subtract x, x squared, or x cubed to get 1. So 1 is a linearly independent vector, and then same thing goes with the x, x squared, and x cubed. And so the last thing we're going to talk about is going to be span and bases. And so given a matrix A, the span of the columns of A is considered called the column space. So pretty creative with the naming. And we can find the non-zero solutions of A of x equal to 0 when the columns A or the columns of A are linearly dependent. So that's just basically saying that we can find like every non-zero solution of A of x equal to 0. So basically the kernel when when the columns in A are linearly dependent. So that means you can write them as a linear combination of another set of vectors. And then the last thing we're going to talk about is bases. And so if we have a set vector, we're going to use the same one from the last slide, so v1 all the way to vk. If we can say that vector is a basis of vector space V if and only if the vectors are linearly independent and they span V. So it pretty much checks two conditions, and they pretty much go hand in hand. So if it's linearly independent, then they can span that vector. And so if we check that a set of vectors are independent from each other, and we also know that they span in that vector space that they're in, then you can consider that set of vectors a basis of V. And a basis is a minimum spanning set for V. So what that means is that the bases can also be, or the bases span V, but there is some vectors that span B or span V but are not a basis. So if that set of vectors is a basis of the vector space V, then any set with more than n elements must be linearly dependent. So what that basically means is if you have a set that contains, or a set that is a basis for a vector space, and that set has 3 elements, if you create another set that has 4 elements, then that 4th element becomes redundant. So that means that that 4th element can be written as a linear combination of the other 3. And so a good example to put this is when you're working with a two-dimensional coordinate system. So you have your x coordinates and your y coordinates, and so that's going to be, we can say it's going to be 0 1 and then 1 0. If we have another, and so that's going to be in our set, so 1 0 and 0 1. If we have another set that is 1 0 0 1 and then 2 3, 2 3 is, or must be, linearly dependent, because we can write that as a linear combination of the 1 0 and 0 1. So that will mean that you can write it as 2 times 1 0 plus 3 times 0 1, and you get the new point 2 3. And then the same thing goes if you go like a higher dimension. So 3 dimensions, you have your x, y, and z. So that'd be your 1 0 0 0 1 0 and then your 0 0 1. If you introduce a new point in the set, it doesn't matter what point it is, you can write it as a linear combination of those 3 points that I mentioned in the first place, or yeah, those 3 points that I mentioned. And so that's what it means by a basis having the minimum spanning set, because that's the minimum number that you can create to have a span of V. Obviously it could be higher, but consider the basis more as like the most simplest span of a vector space. And then anything else that you create given that basis would be a linear combination of those vectors in that basis. And then the common number of vectors in every basis of a vector space is called the dimension of V. So when I go back to the xy plane, we have 2 vectors there, 0 1 and 1 0, or 1 0 and 0 1. That means the dimension of V is equal to 2. When you move up to the 3 dimension, it will be x, y, and z, each respectively having 1 0 0 0 1 0 and 0 0 1. The dimensions of that basis will be the dimensions of V, which would be 3. And then if you go on like higher dimensions like 6 7 8 9, their dimensions would be 6 7 8 9 respectively. And so that's pretty much it for this video. We are going to do a couple examples on how to find bases, and as well as checking if certain vectors are independent from others, and as well as trying to find a linear combination given a span. So I'll see you guys in the Blackboard.